Right. Welcome you to this lesson. I'm Mr. Ripper, and we're going to cover chemical properties of carbonyl compounds. When we talk about chemical properties of carbonyl compounds here, we are going to look at these carbonyl compounds undergoing several reactions, which reactions include nucleophilic addition, condensation reactions, reduction, oxidation, and many others. But without wasting any single minute, I want us to start immediately with the nucleophilic addition reactions. Nucleophilic addition reactions. What makes organic chemistry seemingly abstract to some students? It's simply because we do not know the meaning of some words. We do not know the meaning of reactions. That's why I'm planning to prepare a video or a lesson that talks about the types of reactions and the types of reagents, so that when you're doing any mechanism, when you're outlining the nature of the reaction, you be sure of what you're doing. Now, nucleophilic addition reactions here, it means we are having a word nucleophilic, which is a derivative of a nucleophile. We're having the word addition, meaning we are putting. So nucleophilic addition involves addition of a nucleophile to a carbonyl compound. But we want to see why do carbonyl compounds undergo nucleophilic addition reactions? Right? Why do they undergo nucleophilic addition reactions? Why do they undergo nucleophilic addition reactions? When you look at a carbonyl group, you realize that these two have got different electronegativities. Carbon and oxygen have got different electronegativities. A question can come when they can ask you that amongst these questions of stating or explaining the observation, they can ask you carbonyl compounds undergo nucleophilic addition reactions, while some certain group of compounds do not, or like alcohols do not. So you need to be very, very, very careful. So when you're talking about nucleophilic addition, the first observation you should make is the difference in electronegativities of these atoms involved. The moment there is a difference in electronegativities, then that one would mean that if there is a difference in electronegativities, then there would automatically be, the bond would be polar. When there is a difference in electronegativities, the bond becomes polar. But though there is a difference in electronegativities, to what extent? Oxygen is more electronegative than carbon. Oxygen being more electronegative than carbon, it means that the bonds, the electrons in the double bond are attracted more to oxygen than carbon. So since more electrons are attracted to oxygen, it means that oxygen is gaining electrons and it becomes partially positive, while when electrons are leaving, it becomes partially negative. Sorry. Electrons are leaving carbon, so it becomes partially positive, and the oxygen becomes partially negative, making the carbonyl group polar. Thus, the carbon now is electron deficient. And since nucleophiles are electron rich, it means that they can easily attack the carbon, right? They can easily attack the carbon. So basically here, we simply talk about the electronegativity. So if you are told to explain why they do undergo nucleophilic addition, just we talk about the electronegativity. So you would say this is due to the high electronegativity of the oxygen atom, and thus electrons in the carbon-oxygen double bond are attracted more towards oxygen atom, resulting into a partial negative charge on the oxygen atom and a partial positive charge in the carbon atom. This makes the bond polar. You draw this showing me. Then you continue and say, thus the carbon in this group, or the carbon atom of this group, is electron deficient and is readily attracted by electron-rich species, or the nucleophiles. Thus, aldehydes and ketones undergo nucleophilic addition reactions. Some of these nucleophilic reactions are, the nucleophilic reagents that we use, because if the reaction is nucleophilic addition, then it means that we need to know those nucleophilic reagents that are involved in this reaction. So some of those nucleophilic reagents involved include hydrogen cyanide, they include the cyanide, they include sodium hydrogen sulfite, they include derivatives of ammonia, and those derivatives of ammonia can be the hydroxylamine, they can be phenylhydrazine. It's one word, phenylhydrazine. We have 2,4-dinitrophenylhydrazine, dinitro. Then we have hydrazine. So we are going to look at how carbonyl compounds react with all these one by one. But in this video, I want us to start with hydrogen cyanide and sodium hydrogen sulfite. Then in our other video, we cover the rest. But we've said that there are other types of reactions apart from nucleophilic addition that we are going to look at. So let's look at addition of hydrogen cyanide. Hydrogen cyanide. Now, when you talk about hydrogen cyanide, this reaction, one can call it cyanohydrin formation reaction, because we form a cyanohydrin. Cyanohydrin formation. Now, aldehydes and simple ketones. Okay. they react with hydrogen cyanide at temperatures of 10 degrees to 20 degrees Celsius, right? And here we form 2-hydroxy alkanonitriles, or what we call the cyanohydrins. From cyanohydrins, all right? Now, the hydrogen cyanide that we use is prepared in situ from the reaction between dilute sulfuric acid and potassium cyanide, okay? So, yeah, the reaction between the potassium cyanide and dilute sulfuric acid is the one that leads to the formation of these compounds. So, one can have a look at examples, because we shall be outlining the mechanisms, examples. Each can be CH3, CHO. One can give you potassium cyanide and dilute sulfuric acid at a temperature of 10, 20 degrees Celsius. All right? You can have such a reaction, or they can give it to you direct. They can give it to you direct, CH3, CHO, plus hydrogen cyanide, direct. So sometimes you find someone is not sure at all about the reaction mechanism. And in the case where you're not sure about the reaction mechanism, it's rather about the product. You can first write the equation for the reaction. And first write the mechanism, and then afterwards you can proceed. So in this mechanism, we shall have hydrogen cyanide, because even if it is this, it will give hydrogen cyanide. So just have hydrogen cyanide dissociating to give hydrogen ion and a cyanide ion. The minus can the minus is on C, cyanide ion. The minus is on C. So now, what happens is the fact that you already know that the carbon is partially positive and oxygen is partially negative. This one can be rearranged as CH3, then C, oxygen is there, while hydrogen is here. So you know that this is partially positive and this is partially negative. So what happens is that we shall bring our cyanide ions, right? We shall bring our cyanide ions, because a cyanide ion is a nucleophile. So that cyanide ion will come as this bond breaks. So this one will lead to the formation of CH3C O minus, shall have O minus, then shall have this hydrogen. I can put it down here, and then Cn. All right, then Cn. So addition of this hydrogen can lead to the formation of cyanohydrin, CH3C. Now this one we shall form a hydroxy. Then we shall have H here and Cn here, implying that your product would be CH3 COH H, then Cn. That is what we would form. One can outline this mechanism also in another version. One can outline this mechanism in another version. One can have CH, one can have C, double bond O, partially positive, partially negative. Then we had the CH3, so it is H3C, and then we have the hydrogen. So you bring your cyanide ion, and then one bond here will break. So here we shall form H3C, carbon, H, you have attached a Cn, then O minus. Then at this point, you bring the hydrogen. Right, you should mind your bonds. Your bonds should not be waves, okay? So here we shall form CH3, C, OH, Cn, then H. And this is read as 2. Can read it as 2 hydroxypropanonitrile. Hydroxypropanonitrile. Right, all right. Then that is an example of an aldehyde reacting. Then what about if we have a ketone? If we have a ketone, for example, CH3, C double bond, or then CH3. If it is reacting with potassium cyanide in an acid, meaning sulfuric acid. So this is used to prepare the hydrogen cyanide. So this is hydrogen cyanide in this case. So what we do, I may not be sure of the product, but if I'm sure, I can write CH3, C, then OH, then Cn, then CH3. Then the mechanism would be, you have C, double bond O, for this case. Then I have two H3s attached, H3C, H3C. So bring your cyanide. because you have to first show me that this is partially positive and this is partially negative. So when you bring this, excuse me, this arrow goes to carbon. It goes to carbon. It must go to carbon, which is electron deficient. And this one being in nucleophile, which means that electrons are going to carbon. Then a bond breaks here. And there you form H3C, H3C, then CN has come on the carbon. Then now we have one bond, or minus. Then you bring the hydrogen. This hydrogen is from hydrogen cyanide. So you're going to form your final product, CH3, C, CN, CH3, then OH. And this is what we call 2-hydroxy 2-methyl propanonitrile. Propanonitrile. Right, that is what we have. Those reactions. So one can also have now this reaction here is very slow. So if one wants it to be rapid, you can carry it out in presence of an alkali. Okay, you can carry it out in presence of an alkali. It can be very, very, very rapid. So if you have another compound like this, CH3, CH2, C, or then CH3 reacting in presence of hydrogen cyanide, and now an alkali. We shall put an alkali to speed up the reaction. So OH, if you have something like that, having that, it means that if I'm outlining the mechanism here, I'll have, of course, the final product will be CH3, CH2, C, OH, then CN, then CH3. So the mechanism of the reaction, I will have CH3, CH2, C double bond, then CH3, of course, having a cyanide, I can have, as this one goes, that's what you need to know. So here, I will form CH3, CH2, then now C, with one bond, or minus, because electrons are being given to oxygen, so minus, then I will have my Cn here, then my CH3. So what happens is that the OH which have involved, I can bring it here, or still, we've said that the presence of a hydroxide group is to speed up the reaction. All right, so we are going to have our hydrogen added still to form the final product, because you see that what you need here is the hydrogen, right? What we just need is the hydrogen. So it means that the hydrogen in the cyanide is going to come and attack the O, then still will form our product again, like though we were doing. So like any other nitrides that we form, the cyanohydrins formed can be hydrolyzed, and when they are hydrolyzed, we form hydroxycarboxylic acids, right? These cyanohydrins we formed, for example, like CH3, CH, we add OH, and CN. They can be hydrolyzed, okay? And we can hydrolyze them in water, right? Or you can hydrolyze them using conc hydrochloric acid and reflux at 50 from the carboxylic acid. So one can use conc hydrochloric acid and reflux at 50 degrees Celsius. You form the hydroxycarboxylic acid. So you form CH3, COH, then COOH, then H. So this is what we call 2-hydroxypropanoic acid, 2-hydroxypropanoic acid. That is what we form. So Na, you can still get the same thing. Still, yeah, basically this is enough. This is enough. Even other examples, just where there is CN, you put a carboxyl group. Then that one is done. So let's look at the second reaction, which is addition of reaction with the sodium hydrogen sulfide. Reaction with sodium hydrogen sulfide. Now, we shall realize that these most aldehydes and methyl ketones react with excess sodium hydrogen sulfide at room temperature to form white crystals, which are formed as addition products, right? So Also, I can write and say maybe when aldehydes and ketones are shaken with the saturated solution of sodium hydrogen sulfide at room temperature, they react to yield carbonyl hydrogen sulfide, which is isolated as colorless crystals. E.g., you can have CH3 CHO, that is ethanol plus sodium hydrogen sulfide. We have said that we form the carbonyl hydrogen sulfide. So it is CH3 CH. After reaching here, we shall form OH, then SO3 minus, then Na positive. So that is what we call a carbonyl hydrogen sulfide. And let's see how we write the equation. Let's see how we write that equation. So for the case of the mechanism here, that is the equation. The mechanism would be, first of all, the sodium hydrogen sulfide will first dissociate from sodium ions and the hydrogen sulfide ions. Right? From sodium ions and hydrogen sulfide ions. So, what takes place now is that, of course, you know how that carbonyl group is arranged. So, you arrange it such that you have CH3, then C double bond O, then H. This is partially positive, this is partially negative. So what happens is that bring the hydrogen sulfate, you bring the hydrogen sulfate. So when you bring the hydrogen sulfate, it is going to be a sulfate. I can write it as S because we have 3 oxygens. So that is 1 oxygen, but with an H. So we shall have H also. There are two ways of writing this mechanism. Then here we have got another oxygen. All right, then we have another oxygen. So I have it like this. So what happens is the lone pairs on oxygen will come on this, while this one will come here as the oxygen goes, the bond, as one bond goes there. So in this case, we shall have CH3, CH with the O minus, because electrons have been gained, but also it gains a negative charge. Then here, since the sulfur came on carbon, so we shall have sulfur, double bond here because a bond came here. So we have a double bond, then another double bond, then the O, then the H. There comes hydrogen shift. All right. Here comes hydrogen shift. I have to put double arrows, and we talk about hydrogen shift. So when we put hydrogen shift, it means that we shall form that hydrogen will shift to this. So here we shall have OH. So we shall have CH3, C, H, OH now, S, O, but hydrogen shifted, so this one is unstable. Then O, then O. Then now here we add a sodium ion. All right. So at this case, we shall add sodium ion. And when you add the sodium ion, you form the end product. Which end product will be, according to what we've written here, it is a CH3. You can write it, though it may appear different in arrangement, but they are the same. You have C, then OH, now I can bring this H down here so that I have H. Then CH, then I can put SO3 with minus, and then sodium. We added sodium ion, so sodium ion plus. This is our final product. This is our final product. This is the first mechanism one can outline. All right. Alternatively, one can have CH3, C double bond, or H, partially positive, partially negative oxygen, partially positive carbon. So we can bring in sulfur or OH. I'm trying to write iodine sulfur. Then, or I can have Na. I can bring all of it together, the sodium hydrogen sulfate, all of it together, sodium hydrogen sulfate. So now, what happens is that this bond here comes over here, as the lone pairs of this come there, and as this bond breaks, forming CH3C, then H, I will have H here. This H, I will put it here. Then, since one bond broke off, so I have O minus. Right? I have O minus, but remember, I broke the whole molecule, so I can say O minus Na plus, since I broke the whole molecule, then I say S with a double bond on oxygen and another double bond, which is this, then with OH. All right, and this one, when you rearrange, we shall form CH3, C, O, H, then H, SO3 minus Na plus. A bit tricky here. I brought the whole molecule, so you can prefer using the one that is easier for you. So let's look at another alternative. And this alternative, rather another example, we are going to consider CH3. Another example, let me say CH3 COCH3 sodium hydrogen sulfate. Let me first outline the mechanism. That is when it can be easy. Say that you first dissociate sodium hydrogen sulfate. When you dissociate it, you will form sodium ion and the hydrogen sulfate ion. So you bring your compound. I can write it as CH3 2 times, then C O. I can still write it like that. Then I bring my hydrogen sulfate ion. So I'll bring S. I can have my O here. I can have my O minus here. And I can have my OH here. So you can arrange this compound, you can arrange the hydrogen sulfide in different ways. So what happens is that the lone pair, of course, this one will come here, while the lone pairs on sulfur will come over here as this one goes. You know the reason. Carbon is partially positive, therefore it is electron deficient. So what we form is CH3 times 2, then C, O minus, then SO3 with H. So we shall have hydrogen shift. With hydrogen shift, we shall form CH3. 2 times, then C. When hydrogen shifts here, we shall have OH. And this one will keep SO3 minus, because hydrogen shifted from this side. So we shall have SO3 minus. Then we add sodium. And we shall form CH3 2 times, then C, then SO3 Na, because you have added sodium, then OH. This is propanone hydrogen sulfide, because we said we form carbonyl hydrogen sulfide. So we form propanone hydrogen sulfide. So one can now bring the product. You see, in this case, I began with the mechanism, but sometimes that students forget the product after beginning with the mechanism. They forget going back, put the product. So OH. That is it. Now, in this case, we are going to have all viewers attend to this. All viewers attend to this. Complete and write the mechanism. CH3, CH2, CHO. Reacting with sodium hydrogen sulfide. This one brings us to the end of this lesson. And now, in our next lesson, we shall look at the reactions with the ammonia derivatives. See you there. Good time.